भगाएं। थोड़ा सा हम लोग का एक अगर इन्फेक्ट हो जाता है तो उससे 5000 पीपल में गेट इन्फेक्टेड। 5000 लोग उसका साथ कांटेक्ट में आके इन्फेक्ट होने की संभावना है। तो यू कीप योरसेल्फ सेफ एंड कीप अनदर 5000 सेफ। तो आपको ये सावधानी, यू हैव टू टेक द केयर, बी केयरफुल एंड don't don't move out with, because the environment is heavily polluted, particularly Delhi zone। और एमपी भी उतना कोई खास अच्छा नहीं है, और लोग मानते नहीं है, लेकिन जो नहीं मानते हैं उन लोग को आफत आ जाता है। जो लोग बात नहीं सुनते हैं उन लोग को प्रॉब्लम आ जाती है। एंड प्रॉब्लम जब थोड़ी सी बढ़ जाती है, कोई मेडिसिन रेस्पॉन्ड नहीं करता है, नॉट ए सिंगल मेडिसिन। इनिशियल स्टेज में अगर उसको चेक कर लो तो ठीक, नहीं तो थोड़ी सी अगर ऑक्सीजन लेवल कम हो गया तो नो मेडिसिन वर्क्स, नो मेडिसिन वर्क्स। ये है इसकी जो वायरस की सबसे बड़ा खतरा। इनिशियल स्टेज में इसको रोक दें तो ठीक, नहीं तो वायरस बहुत जोर से पंगा कर लेता है। ओके ओके, सो माय डियर चिल्ड्रन, टेक केयर, डोंट बी कैजुअल, केयरलेस, अपने आप को बचाओ। और ऐसे तो 2-3 हम लोग का सीख है। आज मैं देख रहा हूँ ये गुप्ता आया है ना। गुप्ता, हाउ इज योर हेल्थ गुप्ता?
Yes, sir. I'm good now, sir.
देखो क्या तुम्हारा क्या हुआ, तुम क्यों एडमिशन तुम्हारा हुआ?
Sir, actually, some part of liver also get affected by corona, sir.
ओह ओह ओह, तब अभी क्या बोले डॉक्टर अभी?
सब सब मेडिसिन चल रहे हैं सर, एक हफ्ते बाद फिर से सीटी स्कैन के लिए बोले हैं।
ओह भगवान,
लीवर थोड़ा कुछ अफेक्ट कर गया है वो।
ओह ओह ओह, आई एम रियली सॉरी, रियली वरीड फॉर यू, रियली वरीड। लेट एवरीबॉडी प्रे फॉर आशुतोष, he should be cured at the earliest। ओह, और डालमिया की क्या हालत? डालमिया ज्वाइन किया? डालमिया आज डालमिया ज्वाइन? नो, डालमिया हैज टू ज्वाइन। ओह, शिवम डालमिया, he has joined I think। शिवम कहाँ टट्टी करने गया ना, कहाँ गया टट्टी करने? शिवम not able to, maybe net problem। Okay, so he was sick like you, like Asutosh, he was also sick। Oh, so I feel very much worried because this virus is highly dangerous, highly dangerous, highly dangerous। ये बात मेडिसिन को रेस्पॉन्ड नहीं करती है। ओके, so take care, we are not meeting on Saturday, we will be meeting on Monday 4:15। okay okay, so we will start। इंगोले,
Yes, sir.
या तुम्हारा जोर, टोन थोड़ा ज्यादा बढ़ा, पिच।
Yes, sir.
ओके
Yes, sir.
ओके बेटा, चलो।
We have completed the first 2 points, the concepts and examples, and we have seen the 2 examples. The first one was of pipe and filter, and the second one we have completed is C2 style. So now we will see the application. So here we will implement the lunar lander in different frameworks. So we will implement it in pipe and filter, and we will implement it in C2 style. So, okay, so we will start the third point application, implementing lunar lander in different frameworks. So this is the architecture of our pipe and filter lunar lander. So we have 3 components, 3
आप
filters.
चेंज करो इंगोले, नेक्स्ट
Change नहीं हुआ है.
स्लाइड आया नहीं, नेक्स्ट स्लाइड आया नहीं, नेक्स्ट स्लाइड।
Just wait.
ये ना, ये नहीं ना।
Sir, I am uploading just.
ओके, अपलोडिंग, ओके ओके ओके, अपलोडिंग, इज अपलोडिंग। हाँ 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 हाँ
It's changing now?
हाँ it's changing. Yeah,
Yeah.
it's
Okay.
हाँ हाँ ये वाला right.
Here we will implementing our lunar lander in pipe and filter. So we have three main components here. We will call it filter. So we have get burn rate, we have component compute new value, and we have display new values. So these are our three filters or components, and they are connected by stream connector. So we are looking in java.io framework, so implementing as a multi-process application. Each component filter will be a separate OS process. So we have these three separate components filters. They will be a separate OS process. Operating system will provide the pipe connector. So OS will be providing us the pipe connector. Going to use just the standard input and output stream. So we are just using the standard input output stream and we are ignoring the standard error. So ignoring good error handling practices and corner cases for simplicity. So for the simplicity purpose, we are just considering the standard input and output stream. So a note on IO. So some messages sent from components are intended for output to the console to be read by the users. So here the third component you can see display new values to users. So some messages will be sent to these components and which are intended for output to the console. These messages must be passed all the way through the pipeline and output and at the end. Suppose this first component get burn rate from user, it will send some message to the this last component. So this middle component compute new value. The only purpose it will do it will pass the values down to the last component. So these messages must be passed all the way through the pipeline and output at the end. We will preface this with a hash. So the messages starting with hash, no computation will be done on these messages. They will be only for display. They will be passed to the last component. And some messages are control messages meant to communicate state to a component down the pipeline. The messages which start from this percent sign, those will be used for computation purpose. These messages are intercepted by a component and process. So starting with hash, they are only for displaying, and starting with a percentage, those are for computation purpose. So we will preface this with a percent. So keep this in mind that we have a hash and a percent. So now we will implement one by one the first component first, the second component, and then the last component. So the first component we have is get burn rate component. This component, the first one. So the loops on each loop. So it will be on loop. These 4 points will be in loop. So the first point is prompt user for new burn rate. So it will ask for the burn rate, read burn rate from the user on standard input. So what the user will input the burn rate, send burn rate to next component. So after entering the burn rate, it will be sent to the next component and quit if burn rate is less than 0. So simply it means that it's asking for the user to enter the burn rate. If the burn rate is less than 0, quit, and if the burn rate is greater than 0, pass it to the next component. So this is the functionality we are implementing in get burn rate component or filter. So it's implemented in Java. It's a Java code for get burn rate. Here you can read the comment. So as you run this program, so what you can do is you can copy this program into a get burn rate and you can try to run it. It will run. So I have tried it. So as you run this program, you will get a message, welcome to Lunar Lander. Then we have an input stream reader to get the input from the user. So you can see here set initial burn rate to 0. So we have initial burn rate 0. You can see int burn rate 0. Then it will show us that enter burn rate or less than 0 to quit. So it's asking us to enter the burn rate. You can see the last line system.out.println. So it will be displayed on the console. Enter burn rate or less than 0 to quit. So we have two options. We can enter the burn rate more than 0 or less than 0 to quit. Here you can see the first line string. So here you can see the comment read user response. So string burn rate string is equal to input dot read line. So this line will take the input from us. Input dot read line. So here we are giving the input. So converting it to the integer burn rate. We are taking the burn rate here. And now here you can see send user supplied burn rate to the next filter. We are taking the burn rate. We are sending it to the next filter. And you can see it's in a while loop. So while burn rate is greater than 0, as we have seen, it's in loop. On each loop we are taking the burn rate from the user. If it's greater than 0, continue the loop. If it's less than 0, end the loop. So the same thing is here. You can see it's a do while loop. So it will check if the burn rate is greater than 0, it will continue the loop. If it's less than 0, it will close the loop. It's a simple program taking the burn rate from the user. If greater than 0, pass it to the next component. Less than 0, quit. That was the first component, get burn rate from user. The second component we have is calculate new values. Calculate new values component. So read burn rate from the standard input. First thing. Second is calculate new game state, including game over. So as we have seen, the first component is sending the burn rate to the second component. So we are reading the burn rate from the standard input. Then we are calculating the new game state, including game over, and send the new game state to next component. So here what we are doing is we are calculating the game state, and we are sending the state to the next component. In the previous component, we have accepted the burn rate. In this component, we are calculating the game state and sending this game state to the next component. So now new game state is not sent in a formatted string. That's the display component's job. We are not sending the game state in a formatted string. That's the display component's job. So here the main thing we are doing is calculating the game state. In the first component, we are accepting the burn state, forwarding it to the second component. Here we are calculating the game state. We will see the code here. So here are some values we have initialized. So we have final int gravity 2. Final means we can't change the value now. It's a constant. Then we have altitude 1000, fuel 500 liters, velocity and time. So these are the initial values you have provided. Again, we have created a buffer reader to accept in the values. So as you run this program, you will see these 4 statements. So it will show that how much is the altitude, fuel, velocity and time. So simply it displays we have this much of altitude, fuel, velocity and time. So here we are accepting. Here you can see read line, input to the dot read line. This line accepts from the user. So the next we can see you can read the comment. This is the status line of text and should be passed down the pipeline. So we have seen. Let me go to the previous slide. The hash and percent symbol. These two symbols. So the hash symbol is just to pass down the line. No computation required. Percent sign computation required. So here you can see if input line dot starts with hash. If it's starting with hash, this is a status line of text and should be passed down the pipeline. No computation required. And if it is starting with percent, this is an input burn rate. So if it's starting with percent, we are using it for computation. So if I enter percent 50, so means I am using 50 liters of the fuel. So it's the burn rate. So here you can see it's a try catch block. So we have burn rate entering it is equal to 50 liters. Then there is condition altitude is less than equal to 0. So if it's less than 0, the game is over. So our lunar lander has crashed. And else if burn rate is greater than fuel, so burn rate is greater than fuel means we have not enough fuel. So sorry, you don't have that much fuel. So we have less fuel. So if the burn rate is greater than fuel, the burn rate is greater than fuel, we are saying sorry, you don't have that much fuel. Here we are accepting the burn rate only. We are taking the burn rate. It is starting with percentage. Percentage 50, percentage 100, whatever you enter. There are some calculations. Calculate the new application state. As we have seen here, we are calculating the game state. So time, we are adding 1. Altitude, we are calculating. We are calculating the velocity. We are updating the fuel minus burn rate. Then we are saying if altitude is less than 0, there are two conditions to land the lunar lander safely. So the altitude has to be 0, means it is landed, and the velocity should be less than 5. So if the altitude is equal to 0 and velocity is less than 5, then you have landed safely. Otherwise, you have crashed. Here we are printing the new values. So whatever values we have calculated, altitude, velocity, fuel, here are the values. Altitude, fuel, velocity. And again, it's a while loop. Time is not equal to learn, and then altitude is greater than 0. So it will be in a loop.
After the class, you please check it, how the program, the steps, the loop, how that is working. Please check yourself in your notebook. Make note.
Yes, sir, you can copy this code and it will run. I have tried this, it will run, sir. So you can copy this code in the Java file and try to run it.
So he has tried. You see, Ingole Bhaiya has tried. Ingole Bhaiya has tried. So you please also try. Until unless you try, you won't understand. So to have a proper understanding how the implementation is done, you have to do by yourself. जो नहीं सीख करेगा वो नहीं सीखेगी. You have to do yourself. Okay.
We have implemented the first two components, compute new values and get burn rate from user. Now the third component, display values component. So read value updates from standard input, format them for human reading and send them to standard output. So it's just for a display purpose. So the first one, get the burn rate from user. Second one, compute the values, and third one, display them. So we have a buffer reader. We have created a buffer reader accepting the input. Input line is equal to input. The reader dot read line. So if input line starts with hash, this is a status line. As we have seen, hash and percentage. Hash is a status line. So this is the status line of text and should be passed down the pipeline with the pound sign strip off. We are removing the pound sign, and then here you can see a switch case is there. Switch value type. So according to the switch case, so if you type percent a, percent a, percent of, percent b, percent a, any of the input, so we are stripping off the percent sign and we are switching according to the next sign. So if you have a, we are going to altitude. You have f, fuel, v for velocity, and t for time elapse. So these are the four switch case we have. And again, it is in a loop. Now we have the three components. We have the code for three components. So the first is java.getBurnRate. So this is the first Java file. The second is Java calculate new values. Second Java file, and third file is Java display values. So you can copy this code in the respective Java files, compile the files, and then in the command line write this Java getBurnRate, this symbol, Java calculate new values, this pipe symbol I think, and Java display values. You will get this console. So here you can see. So here you can see the command Java getBurnRate, the previous command only, Java getBurnRate, pipe symbol, Java calculate new values, pipe symbol, and Java display new values. So here you can see. So the same thing will appear after running this program. Here you can see altitude 1000, fuel remaining 500. This is the initial state. We have at altitude of 1000. We have fuel of 500. So current velocity is 70, and time elapsed is 0. So welcome to lunar lander. Enter burn rate. So this is of the first. So here the main thing is all three components are running in parallel. The first component, third component, and the last component are running in parallel. So we are entering the burn rate. So you can see enter burn rate or less than 0 to quit. You can see the 50 value under it. So after that entering the burn rate, it has calculated the new state. So you can see the difference in the first 4 lines and this next altitude, fuel, current, velocity and time elapse. So you can see the altitude has decreased. It is 930 now. Fuel remaining, you can see we have burn 50. So it's 450. The velocity has decreased to 62 and time elapse is 1. So again, we are entering the burn rate. So it's 100 now. Again, you can check the altitude has decreased. The fuel remaining is 350. You can see 100 liters we have burned. We have current velocity is 44, decrease, time elapse 2. So similarly, we keep on going. Now here you can see the crash condition. So enter burn rate is 0. They have enter. So altitude is 0. Altitude is 11. We have no fuel. Velocity is 26. Time elapse is 28. So the here what happened is you have crash. So because the altitude is 11, fuel we don't have any fuel. So like this, you can keep on entering the values. These 3 components. Okay, so this is for the lunar lander in pipe and filter. So what are the takeaways? So Java IO provides a number of useful facilities. So we have stream objects to system.in, system.out to read the values, to pass on the values, system.out. We have buffering wrappers. So we have seen the buffer reader, all those. And OS provides some of the facilities. So the pipes are provided by the operating system. And we have concurrency support. So as I have told you, all these filters are running in parallel because this command java get burn rate. So all these 3 filters are running in parallel. We are not running a program separately. We are running all the programs simultaneously. So concurrency support. Note that this version of the application will not work if it's operated in batch sequential mode. So if it's operating in batch sequential, it will not work. It has to be in concurrency. We had other communication mechanism available, but did not use them to conform to the P and F style. We had to develop a new, albeit simple protocol to get the correct behavior. Now we have seen it in pipe and filter. The second example is lunar lander in C2. So here we will see a lightweight C2 framework. So here we have 4 components. We have clock, game state, we have game logic, and we have GUI. And all those are connected to a bus. So we can see each component has its own thread of control. Components receive requests or notifications and respond with new ones. So the components will receive notifications through this bus. Message routing follows C2 rules. And this is the real-time clock-driven version of lunar lander. So it's a real-time, it's a clock-driven version of lunar lander. So we have these 4 main components, filters connected to a bus. So now again, like the previous pipe and filter component, we will start implementing each filter one by one. So the first filter we are looking here is clock. So the first is clock component. So here the clock component, this first one is the clock component, sends out a tick notification periodically. So after so here we have used 5 seconds. So after 5 seconds, it will send out a tick notification. It does not respond to any messages. The only work it will do it will just send out a tick information. So we will see a code for that. After 5 seconds, it will send out tick notification. So here you can see repeat while the application runs. So in the public void run method, you can see while true, wait for 5 seconds. So we are using thread.sleep. So it's a multi-threading concept in Java. So we have thread.sleep. So it will wait for 5 seconds. So 5000 milliseconds it is. So it will wait for 5 seconds. After every 5 seconds, you can see the comment again, send out a tick notification. So you are creating an object notification n is equal to new notification, clock tick, and send n. So after every 5 seconds, we are sending the notification. So the only purpose of clock is sending a notification after 5 seconds. That's the main thing. So again, this component does not handle notification, so this not required. So the purpose of clock is sending a notification, a tick after every 5 seconds. So the next component we will see is a game state component. So this game state component. So what are its functionalities? We will see. So receives request to update internal state. So it will update the internal state. Emits notification of new game state on request or when state changes. So whenever a state changes, it emits notification of new game state on request or when state changes. Does not compute new state. Just a second, guys. Okay. So this game state we have. So what game state will do it? It emits notification of new game state if someone requests or when state changes, and it does not compute new state. It's a data store. It will not compute. It's a data store only. So now we will see the code for game state. So again here we have some initial values: altitude, fuel, velocity, time, and burn rate. So initial values as the previous ones: 1000, altitude is 1000, fuel 500, velocity, time, and burn rate. So here you can see if r.name equals update game state. So we are entering what we want to update. If we want to update altitude, fuel, velocity, time, burn rate, or landed safely. So these are the if statement. So if the parameter is altitude, we are changing the altitude. If the parameter is fuel or velocity, time, burn rate, if all are these are if statements, you can see. So according to the parameter, anyone will be, so that will be executed and send out the updated game state. So notification n is equal to create state notification and send n. So you can see it is sending the new game state only. So it's a data store only, no computation here. Just wait a second. So the next comes here is, you can read the comment again. If a component requests the game state without updating it, send out the game state and create a new notification compromising the current game state. We are sending the what is the state of the game. So the second component, game state. Now we will see the third component, game logic. So the third component is game logic, receives notification of game state change. So when we are changing the state, it will receive the notification. Receives clock ticks on clock tick notification, calculates new state and sends a request up. So after every 5 seconds, the clock will give notification tick, and then on receiving this clock tick, it will calculate the new state. So game logic, it's calculating the new state, and then sends a request up. Again, sends the request into the bus. So the main functionality is this is notification of game state change. It will receive the notification and calculate a new state. That's the main functionality of game logic component. That is to calculate the new state. So here you can see in the state diagram, we have start, send game state request. We are sending the get game state request. So it will take this to the game state. Then we will get the game state request. Then again on a clock tick, we will calculate the new game state. And after calculating it, again send it. Send update game state request. So it will be in a loop. Calculate the game state, send it, again calculate it, send it every 5 seconds. We'll keep it doing. Again the code. So we have internal state values for computation. So we have altitude set to 0, fuel velocity, time and burn rate. So all are set to 0. Then we have public void start method. We are creating a request object after that. So again, as in the previous, there are different if statements. So whatever is the parameter, according to the parameter, we will select the if statement. So if it's altitude, the game state is altitude, fuel, velocity, timer, burn rate. According to that, we will select the if statement. So here as we are calculating the state system, the game state. So here are some calculations. Calculate Newlander state values. So we have actual burn rate is equal to burn rate. So actual burn rate is greater than fuel. Ensure you don't burn more fuel than we have. So we have to keep the burn rate less than the fuel. So increasing the time, again calculating the altitude, new altitude, calculating the velocity, calculating the remaining fuel. Then we are determining whether it is landed safely or not. So the condition we have seen before, altitude less than equal to 0 and velocity should be less than equal to 5. So this is the condition for landing safely. Again creating a request object, adding the parameters time, velocity, and then sending it. Here you can see r dot add parameter. We are adding all the parameters time, altitude, velocity, fuel, and landed safely or not. And we are send r. You can see. So we are calculating the game state and we are sending the game state. And the last component is GUI. So what it will do is reads burn rates from user and sends them up the request. So here we are entering the burn rate from the GUI component. So receives notification of game state changes and formats them to console. And the second thing is it will show us the state of the game. So it's because it's a GUI component. Accept the burn rate and show the state of the game. So these are the two functionalities it will do, GUI component. So here we have a start method. We are creating a new thread. Here you can see we are creating a buffer reader for accepting the input to accept the burn rate from the user. Input reader. So again we are setting the burn rate to 0. Here you can see enter burn rate or less than 0 to quit. Same as in the pipeline filter. So accepting the burn rate, all this code is for accepting the burn rate. And then we are requesting, here you can see string burn rate string is equal to input reader dot read line. So here we will enter the burn rate. And under that you can see request r is equal to new request update game state r dot add parameter. We are adding the burn rate and sending it. So we are accepting the burn rate and we are sending the burn rate so that the new state will be calculated. And again the condition, if it's greater than 0 it will be in a loop. If it's less than 0 in minus, so it will stop. So again new game state, the loops we have seen, not loops, the if statements we have seen before, altitude, fuel, velocity, time and burn rate, all for all these parameter. So again the condition altitude less than 0, it's landed safely, so that condition is here. And if it's not less than 0, so you have crash, and the other is you have landed safely. It will be in a if else statement. Here you can check if landed safely, so you have system.out.println. So after implementing these 4 components, we have clock, game state, game logic, and GUI. So we have a main program, which instance, after implementing these 4 programs, we will have one more program which will connect all these elements. So that will connect all these 4 programs. So we will see that main program now. So we have that in this main program. So here we will see we have here it is written that create the lunar lander architecture. The comment is there. So we are creating a lunar lander object. Then we are adding the four components. The four components we have written. You can see the clock, game state, game logic, and GUI. The four components we have added because we have four separate components and we have to add them together. So this program will do that. So we are adding the four components, creating the four components first. Then we are creating the connector. Connector bus is equal to new connector thread. Then we can see add the components and connect to the architecture. So lunar lander dot add component clock. So our main program is lunar lander. We are adding all the four components: clock, game state, game logic, and GUI. Here you can see all these four components have been added. Lunar lander dot add component clock. Similarly, game state has been added, game logic, and GUI. All these four components have been added. And connectors are also there. So we have lunar lander dot weld clock bus game state. We have bus and game logic and bus and GUI. All this we are adding to the bus. All these components we are adding to the bus. What are the takeaways in for the C2 framework? So here the C2 framework provides most all of the scaffolding we need. So here we have seen message routing and buffering, how to format a message, threading for components, and startup and instantiation. So we provide the component behavior, including a couple of new threads of our own, and we still must work to obey the style guidelines. So not everything is optimal here. State is duplicated in game logic. These are some of the takeaways of our C2 framework. Okay, this is the last slide. So we have seen the implementation in the pipeline filter and the C2 framework. So you can try the pipeline filter framework, how it will run, and you can also try this one, C2 also.
Okay.
Yeah,
So
this is the,
we completed C2, right?
yes,
Yeah,
yes,
that's
C2.
pipe and filter.
Pipe and filter and C2.
Pipe and filter and C2. Okay, okay. These are the basic what? Styles.
Styles.
These are the basic styles. You have read several styles. Out of several styles, these are the two styles, and it gives a framework how to implement the style. How to implement the style, you learned it step by step. You please do yourself. Write yourself in your notebook how it works. You run the program, then only you will know how it works. Otherwise, it will be just a theoretical subject. Ingole Bhaiya is a good student. He has run it in Java and he has understood how it works. So be like Ingole Bhaiya, okay? शुभम भैया की तरह बनो. खुद को करना है. जो खुद नहीं करता है वो सीखता नहीं है. You won't learn at all. You won't learn at all. So do yourself. Okay. Next chapter I think it is on rest ना.
Yes sir.
कर लो. हाँ, applied. अभी हम लोग एक applied कैसे architecture को apply करेंगे. How we will apply it. It is on rest architecture. बहुत कम ही slide है. ये Subham Bhaiya will finish it. Very less number of slides are 20 slides are there, right?
25 slides are, yes sir.
Yeah, something like that. So you please finish it. I have got another meeting. I am quitting. You finish and you take the attendance. Okay?
Okay.
Okay. Okay. So we will study today another chapter, that is applied. How it is considered for applied. We will read a lot. We will read a lot in your next semester on rest. So some glimpse you will get it here. Very, very important. The present society is moving towards REST architecture. Your cloud-based applications are mostly based on REST. You ask question, शुभम भैया को पूछो कैसे cloud-based application REST पर depend करता है. को नहीं पूछने से कोई बताता नहीं दुनिया में. जिसकी जरूरत तो खुद you have to inquire. You have to tell it is my requirement. आप पूछो उनको. Okay? Okay, 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 so go ahead. Go ahead.
Yes, sir.
Okay, go ahead. Very good chapter. Please understand this chapter. It has a lot of application. Next semester we will read a lot on rest and soap. So I based on soap that subject, but it is slowly moving towards rest because it has a lot of advantage. Lot of advantage. So you read it carefully, make note, and understand it thoroughly. And if you have any doubt, ask him. भैया ये कैसा होगा? पूछो. नहीं पूछने से आपकी डाउट अंदर में रह जाएगी. कोई जबरदस्ती इस उम्र में नहीं सिखाएगा जब तक आप खुद नहीं सीखने चाहोगे. ओके ओके इंगोले. ओके शुभम बाय. आई एम लिविंग. यू टेक द अटेंडेंस. ओके
Yes. Yes, sir.
ओके बाय बाय स्टूडेंट्स. बाय. हैप्पी दिवाली टू यू ऑल. बाय.
Same to you, sir.
So we will start with the applied architecture. So what are the objectives? So we have illustrates how principles have been used to solve challenging problems. Usefully means combining elements. We will see some highlight some critical issues, ignoring them at your peril, and the show how architecture can be used to explain and analyze common commercial systems. These are some of the objectives. So the outline of this chapter. So we will see distributed and network architectures. What are the limitations? We will see RESTful services. We will see commercial internet scale applications. Then we will see decentralized application. We see peer-to-peer and web services. Then some interesting domains. We will see robotics, wireless sensor, flight simulators. So the limitations of the distributed system viewpoint. What are the limitations of the distributed system viewpoints? So the fallacies of distributed systems are. Yeah. So fallacies means a mistaken belief. Fallacies, a mistaken belief. So what is the belief about distributed system? Which is mistaken. So the network is reliable. It is not reliable anyway. So the network is reliable. Latency is 0. So these all are mistaken beliefs. The network is reliable. Latency is 0. The bandwidth is infinite. The network is secure. The topology doesn't change. So they believe that in distributed system, the topology never change, but it changes. There is only one administrator. So transparent cost is 0, and the network is homogeneous. So these all are fallacies of distributed system. So architecture in action. So here is a diagram of how a WWW, a web, World Wide Web. So this is the web. So there are some more figures. So they are saying you can say this is the web. So this is also web, and so they have shown some different figures. So client and servers they have shown. So what is the WWW architecture, World Wide Web? So the application is distributed, actually decentralized hypermedia. So architecture of the web is wholly separate from the code. There is no single piece of code that implements the architecture. There is no single piece. There are various codes written, various pieces are there, all together connects to create the architecture. And there are multiple pieces of code that implement the various components of the architecture. Various components combined together creates the architecture. So example is different web browsers. So we don't have a single web browser. We have different web browsers. So stylistic constants. And one of the world's most successful application is only understood adequately from an architectural vantage point. So to understand application, we have to understand it from the architectural vantage point. So the next we will see the 6 REST principles. So this will be definitely asked in the exam. See, write down the 6 REST principles. So we will see one by one. Yeah, there are 6 REST principles. So we will see one by one. The first principle is the key abstraction of information is a resource named by an URL. Any information that can be named can be a resource. So any resource which have name like www dot something dot com. So whichever resource has a name has a URL, it can be a resource. The key abstraction of information is a resource. So the second point is the representation of a resource is a sequence of bytes plus representation metadata to describe those bytes. So how a resource is represented. So by represented by sequence of bytes and again metadata to represent those bytes. In the particular form of the representation can be negotiated between REST component. So you can the second point says representation in sequence of bytes. That's the main point. The third point is all interactions are context free. Each interaction contains all of the information necessary to understand the request. So every interactions are independent, context free. That's the main point to understand. Every interactions are context free. Each interactions are self-independent. They contain all the necessary information to understand the request, independent of any request that may have preceded it. So it doesn't depend on any other request. Context free. The fourth principle is component performs only a small set of well-defined methods on a resource, producing a representation to capture the current or intended state of that resource and transfer that representation between components. So it's saying that components perform only a small set of well-defined methods. So we have resource and the component will perform some operations on the resource and then transfer that representation between the components. So we have different components, we have resources, we do some operation on that and it will be transferred between the components. So these methods are global to the specific architectural instantiation of REST. So it's in a global view, we can say. For instance, all resources exposed by HTTP are expected to support each operation identically. So if the resource is exposed by via HTTP, so those are expected to support each operation identically. The fifth principle, idempotent operations and representation metadata are encouraged in support of caching and representation reuse. And next is the presence of intermediaries is promoted. Filtering or redirection intermediaries may also use both the metadata and the representations within request. So the main point is intermediaries is promoted here. That's the 6th point. And the representation within request or responses to augment, restrict or modify request and responses in a manner that is transparent to both the user agent and the origin server. So intermediaries are promoted like filtering, redirection. It's basically talking about the routers, intermediaries. Then we will see the constants on the REST. So there are 1, 2, 3, 4, 5, 6 constants are there. So the first one is client server. So a uniform interface separates client and server, clients from servers. This separation of concerns means that, for example, clients are not concerned with data storage, which means internal to each server, so that the portability of client code is improved. So we have there is a separation between client and server. So clients are not concerned with data storage. Client will only see the front end, like front end, back end. Clients are not concerned with the data storage, which remains internal to each server. So data storage is part of server and client is not concerned with the data storage. So that the portability of client code is improved. Servers are not concerned with the user interface or user state. So again, server is not concerned with the user interface and client is not concerned with the data storage. So you can see the separation of concerns. Servers and clients may also be replaced and developed independently as long as the interface between them is not altered. So we can change the server, we can change the client independently. The next point is stateless. So the client server communication is further constant by no client context being stored on the server between requests. So whenever there is a communication between the client and a server, so no client context is stored on the server. So each request may from any client contains all the information necessary to service for the request. So whenever a client is sending some request, it is self-sufficient. It contains all the information necessary to service the request, and session state is held in the client. So the sessions you might have heard before, sessions and cookies. So the session state is held in the client. Important to note is that the session state can be transferred by the server to another service such as a database to maintain a persistent state for a period of time and allows authentication. So the third point is cacheable. So cacheable is like cache. As on the World Wide Web, clients can cache responses. Responses must therefore implicitly or explicitly define themselves as cacheable or not to prevent clients reusing state or inappropriate data in response to further requests. Well-managed caching partially or completely eliminates some client-server interaction. Like caching means we are searching something in our suppose in a browser we have entered something, some IP address, and if the IP address is already in our cache, if it's mapped already in our cache, so there is no need to go to the DNS server and fetch what is this IP address for the website name. So that caching is mentioned here. So well-managed caching partially or completely eliminates some client-server interaction, further improving scalability and performance. Next point is layered system. So a client can't ordinarily tell whether it is connected directly to the end server or to an intermediary along the way. As a client, we can't tell we are directly connected to a server or not. There might be an intermediary between the client and the server. So intermediary server may improve system scalability by enabling load balancing. There may be load balancer between the client and the server by providing shared caches. They may also enforce security policies. So no need to go to the end server every time. There will be cache between the client and server. So they will act as an intermediary. So the next is code on demand. It's optional. Servers can temporarily extend or customize the functionality of a client by the transfer of executable code. Examples of this may include compiled components such as Java applets and client-side script such as JavaScript. So code on demand is the only optional constant. It's the optional one. So we will see the uniform interface. So the uniform interface between clients and servers, so is discussed below, simplifies and decouples the architecture which enables each part to evolve independently. The four guiding principles of this interface. So we will see the next figure. There it is clearly mentioned what is the uniform interface. Here you can see an instance of REST. So there is a note written down between this under this PPT. So I will read that note. It's not mentioned here. So it says that process view of the of a REST-based architecture at one instance in time. So it is one instance. A user agent is portrayed in the midst of the three parallel interactions. So these are the three parallel interactions, A, B, and C. You can see A, B, and C are three parallel interactions. The interaction were not satisfied by the user agent's client connector cache. So the first on the left hand side, you can see user agent and that small connector, that cache connector is there. So it's like we are entering something IP address in our browser, but it's not already in our browser cache. So it's not in our browser cache. So this line is that we are not satisfied by the user agent's client connector cache. So it's not in our browser, suppose. So each request has been routed to the source resource origin according to the properties of each resource identifier and the configuration of the client connector. So it is, as it is not in our cache, we are sending it to the server. So then there are three different routes, A, B, and C. So the first one, A, has been sent to a local proxy, which in turn access a caching gateway founded by DNS lookup. So in the first route A, it's a local proxy. So it's not there. Again, it will look up in the DNS server, and it will send to the original server. The first one is like from A to proxy to gateway to original server. The second one is directly to the server without any proxy. B is sent directly to the origin server, which is able to satisfy the request from its own cache. So A is sending through proxy, B is sending through is a direct one, and the C is written that C is sent to a proxy that is capable of directly accessing WAIS, an information service that is separate from the web architecture. So it's an information service and translating the WAIS response into a format recognized by the generic connector interface. So it's a kind of service, it's separate from web architecture. So these are three different routes. Now data elements, what are the data elements? We have resource ID, representation. Resource contains key information abstraction, resource ID, representation. We have data plus metadata. Then we have representation metadata, we have resource metadata, we have control data. So all are these are data elements. Example is specifies action as result of message. Then we have connectors. What are the connectors? We have modern web examples. Client, we have server, cache, resolver, tunnel. All these are connectors. Here you can see at the bottom there are 4 kind of connectors are there. Client connector, client cache, server connector, server cache, server plus cache. The connectors, we have data elements, connectors. Components are user agent, origin, server, proxy, gateway. Is the first one user agent is component, this proxy is component, gateway is component, and origin server. These are components and these are connectors. At the bottom you can check client connector, client cache, server connector, server cache, connector and components. Then we have again the same figure we have discussed. In derivation of REST, the key choices in the derivation include layered separation. What were the key choices? So we have layered separation. A theme in the middle portion of diagram is used to increase efficiency, enable independent evaluation of elements of the system, and provide robustness. So client and server, we have separate concerns so that the efficiency is increased. Independent evaluation will be there of the elements, client and server, and it will provide robustness. And then the second is replication. Left side of the diagram, it's saying is used to address latency and contention by allowing the reuse of information. And then replication is basically caching. And third is limited commonality. It's on the right side, addresses the competing needs for universally understood operations and extensibility. The derivation is driven by the application. So is the diagram. Is there any option to zoom? So here it is derivation of REST. So on the right hand side, we have small common interface directly connected to the REST data element decisions. Then on the left hand side, we can say replicated repository. It's connected to cache. Then between the left and the right, so in the middle we have layered system or virtual machines. So it's connected to client server, layered CS, and we have code on demand. So all these are ending into the REST. So REST, the final thoughts. So REST stands for representational state transfer. In the next semester, we will read about it. REST stands so REST stands for representational state transfer. Style of modern web architecture. Web architecture, one of many in style. Web diverges from style on occasions. Example, cookies, frames. Doesn't explain mashup. There are different architectures. This is one is the REST. The other is SOAP. Different architectures are available. So commercial internet scale application. So Akamai is one of the application, caching to the max. Next is Google. Google distributed file system is also application. Google file system GFS. So we have MapReduce, data selection and reduction, and all parallelization done automatically. So it comes under MapReduce. So some of the architectural lessons from Google. We will see some 4 points. First, in abstraction layers abound. So GFS, Google File System, hides details of data distribution and failure. For instance, MapReduce hides the intricacies of parallelizing operations. So abstraction, it will not show the internal working. It will just abstract layer, hide the implementation. So it hides the details of data distribution and failure. So for example, they have given MapReduce hides the intricacies of parallelizing operations. And the second point is, by designing from the outset for living with failure of processing, storage, and network elements, a highly robust system can be created. So the third point is, scale is everything. Google's business demands that everything be built with scaling issue in mind. So you have to keep it in mind that the scaling issue. We have to scale our business. We have to keep in mind that. And the next is, by specializing the design to the problem domain rather than taking the generic industry standards approach, high performance and very cost effective solutions can be developed. Now, by specializing the design to the problem domain, so by selecting the design according to the problem domain, we can build a very high performance and very cost effective solution. By developing a general approach like MapReduce to a data extraction reduction problem, a highly reusable service was created. So it is already created, MapReduce. Oh, it's the last slide. Okay, I will take the attendance. How many are present? 17 are present. Today's date is 12. 11. So I will call out the name, those who are present. No need to say present. So Andrila Shah present. Akshay Kumar. Ashutosh Gupta.
Present, sir.
Yeah. Ashutosh Gupta. Then Srilekha is present. Somashekar is present. Rishabh is present. Then Jitendra is present. Yeah, Mahendra Kumar. Next is Nirmal is present. Pratik is present. Rahul is present. Next, and Rakesh Kumar. And next is Rakesh Kumar, Ranveer Singh. Shivam Dalmia. And then Shubham Kulkarni. Siddharth. Then last is Vikas Kumar. Okay, guys, we'll close the class. You can leave now.